Hey everybody, this is Mr. Ryan, and I'm just going to, as quickly as I can, I'm going to explain to you the fundamental theorem of calculus. Now actually, there are two parts to the fundamental theorem of calculus, and the one that I'm going to explain right now mostly focuses on integration. Now they both involve integration. That's one of the reasons why it's called the fundamental theorem of calculus, because the fundamental theorem of calculus is able to bring together derivatives and integration into one idea. Okay? But this is the one that is mostly used when you want to solve what is called a definite integral. So if you understand the fundamental theorem of calculus, then definite integrals are going to be a piece of cake for you, okay? And when I say piece of cake, I mean they are going to be easy, not that you are going to get to eat a piece of cake unless you buy a piece of cake and eat it while you do definite integrals, okay? And which I recommend if you like cake and can afford cake. So here we go, fundamental theorem of calculus. Before I show you the fundamental theorem of calculus, I need to explain some communication, some math communication to you. We already understand, we learned when we did derivatives, right? That if a function is, let's say y equals 7x to the third power, that the derivative, we can write it as y prime, right? The prime notation indicates a derivative. And so y prime in this case is 21x squared, the derivative, right? This is communication. This is math communication, written math communication, telling the reader that that is a derivative. Well, we have similar notation if we don't use the y notation, if we say that f of x is equal to 7x to the third power, then to communicate the derivative, we might write f prime of x is equal to 21x squared, right? So the f prime notation indicates that it is a derivative, okay? Now, we're now talking about antiderivatives, so I need to show you a common way of communicating an antiderivative within mathematics. What a lot of people will say is that if you integrate the function f of x with respect to x, then whatever the antiderivative is, we call it capital F of x. So whereas the derivative of f of x would be f prime of x, the antiderivative of f of x would be capital F of x, okay? And so this is just a very common way of communicating within mathematics, within calculus. Similarly, we could say that the antiderivative of g of x is going to be called capital G of x. So all we do is really just capitalize the letter, and then it represents the antiderivative of that function, okay? And if you can understand that, then you will understand what I write when I put the fundamental theorem of calculus up here, okay? So, the fundamental theorem of calculus says this. All right, I'm going to write something up here. It's an antiderivative of sorts. Now, here's the big difference. Antiderivative of f of x, we already know is capital F of x. And I'm sorry, I should have clarified. I'm sorry for all the math police out there that the antiderivative is the capital F of x plus c. I forgot to put the plus c on. But you already saw my video on how important the plus c is, so there we go. Capital F of x plus c, and we're good to go, right? Okay, good. All right, so here's what the fundamental theorem of calculus says. What I'm about to teach you in the next video is called definite integrals, okay? We've already done indefinite integrals. Now we're going to do definite integrals. Visually, when you're looking at a problem, one of the ways that you know that it's a definite integral and not an indefinite integral is that there's extra numbers. And let me show you what I mean by that. This is an indefinite integral. This, I mean, look, this basically looks the same, right? Except let's say there's a 2 down here and there's a 7 up here. There are going to be these numbers at the bottom and the top of the integration symbol. And when you see those numbers, you know that you're dealing with a definite integral, not an indefinite integral. So anytime you see these numbers here, that's a definite integral. So here's what the fundamental theorem of calculus has to do with definite integrals. And what I'm going to do is I'm going to put an a down here and a b up here. And this a and this b, they represent numbers. They're not variables, they represent constants. Okay? So, and what we call these is we call them the limits of integration. That one is the lower limit of integration. All right, that a right there is the lower limit of integration. And this b up here, well, that's called the upper limit. That's the upper limit of integration. Okay, that b. So we've got the lower limit of integration and the upper limit of integration. Now, in most cases, this number down here will be smaller than this number up here. You know, you'll have a -3 here and a 7 up here, or a 0 here and a 1 here. But frequently, and it's okay for the number down here to be smaller, or to be larger than the number up here, but we'll get to that at another time. Okay? But let's understand these are the limits of integration. So here's what the fundamental theorem of calculus says, is that if you have a definite integral situation that looks like this, you know, you got an expression here, a number here, and a number here, that this is equal to capital F of b minus capital F of a. That's it. Now let me show you what this means. Let me try to explain it. The fundamental theorem of calculus says that the way that you solve this thing is capital F is the antiderivative of f. So you find the antiderivative, then plug in the upper limit of integration, get a number, then plug in the lower limit of integration, get a number, and then subtract. Okay? Subtract with the upper limit plugged in minus the integral with the lower limit plugged in. And that'll be your answer. And it's always going to be a number. Definite integrals, the answers are always a number, not a function, not an expression. It should be just a number. Okay? So with that, that's the fundamental theorem of calculus. And so I'll see you in the next video where I'll show you how to actually do definite integrals.